Welcome to our lecture on Fischer Nomenclature. Today, we are going to tackle one of the most fundamental challenges in biochemistry. How do we accurately draw complex, three-dimensional molecules on a flat sheet of paper? By the end of this video, you will understand exactly how to read and draw these molecular maps, a skill that is absolutely essential for your journey in zoology and biochemistry. To understand why we need a special drawing system, imagine you are trying to take a perfectly round globe of the Earth and flatten it out to make a two-dimensional paper map. You inevitably have to distort some shapes. In biochemistry, we face a very similar problem. Molecules like sugars and amino acids have specific three-dimensional shapes that determine exactly how they function in our bodies. Drawing them accurately on a flat page is crucial, but drawing complicated wedges and dashes every single time is exhausting and confusing. This brings us to an elegant solution. To solve this mapping problem, scientists use a special projection for molecules called the Fischer projection. It was developed by the Nobel Prize-winning chemist Emil Fischer specifically to make drawing complex carbohydrate structures much easier. In a Fischer projection, the molecule is drawn as a cross. The intersection of the lines represents a central carbon atom, specifically a chiral center. This standardized system lets us easily see the three-dimensional shape without the clutter of complex 3D drawings. Now that we know what a Fischer projection looks like, we must learn its most important rule. The golden rule of this system is that all horizontal lines represent bonds that are pointing out of the page, towards you. You can think of it much like a person reaching out to give you a hug. Conversely, all vertical lines represent bonds that are pointing away from you, going deep into the page. By strictly following these rules, chemists can instantly look at a flat drawing and perfectly visualize the three-dimensional geometry in their minds. You might be wondering why we need to be so precise about these directions. The answer lies in the fact that biological systems are incredibly picky about the three-dimensional shapes of the molecules they interact with. For example, your body can easily digest and extract energy from D-glucose, but it cannot process its mirror image, L-glucose, at all. Fischer nomenclature allows us to instantly tell the difference between these mirror image molecules, known as enantiomers, just by looking at which side the hydroxyl groups are placed on the vertical chain. Before we look at the mathematics of naming, we must establish how to orient our drawing. To properly draw a Fischer projection, we must follow a strict set of orientation rules so that everyone draws the molecule the exact same way. First, we align the main carbon backbone vertically along the page. We must place the most highly oxidized carbon atom, which is usually an aldehyde or ketone group, at the very top of this vertical chain. We then number the carbon atoms, starting from the top and moving downwards. With our molecule oriented correctly, we need to know which carbon dictates the overall configuration. The configuration of the molecule as either D, dextro, or L, levo, is determined by a simple mathematical rule based on the total number of carbons. The formula is C reference equals C sub n minus 1. In this simple formula, the symbol N represents the total number of carbon atoms in the main backbone of the sugar molecule. The expression C sub n minus 1 tells us exactly which carbon atom we need to look at to determine if the molecule is the D form or the L form. If the total carbons increase, our reference carbon simply shifts down the chain. Let us apply this formula to our very first example. We will look at D-glyceraldehyde. This molecule is the simplest aldose sugar in biochemistry, containing exactly 3 carbon atoms. We are tasked with finding its reference carbon. We know the total carbon count is 3, so we set N equal to 3. Plugging this into our formula, we subtract 1 from 3. This gives us carbon number 2 as our reference chiral center. This means the second carbon will dictate the D or L naming for the entire molecule. Now that we have identified our reference carbon, let us prove how the full Fischer projection is constructed step by step. We are tasked with building its 2-dimensional projection from scratch. We know we have a vertical chain of 3 atoms. According to the strict rules of Fischer Nomenclature, we must place the highly oxidized aldehyde group at the very top of our vertical axis. This is designated as carbon number 1 in our numbering system. This anchors the rest of the molecule and gives us a starting point for drawing. Continuing our derivation, we move to the middle and bottom positions. Carbon 2 is our central chiral carbon, which is the heart of the Fischer projection, where the horizontal and vertical lines intersect. Because we are specifically drawing the D isomer of this sugar, we must place the hydroxyl group on the right side of the cross. Consequently, the hydrogen atom is placed on the left side. Finally, the terminal primary alcohol group completes our 3-carbon chain. Following the rules, this group is placed at the very bottom of the vertical axis. By stacking these 3 components vertically, we have successfully created the complete Fischer projection. Let us visualize exactly what we just derived. On the screen, you see the transformation of D-glyceraldehyde from its 3-dimensional reality into our 2-dimensional map. Notice how the horizontal bonds in the 3D model on the left are coming forward, represented by thick wedges. When we translate this to the Fischer projection on the right, those forward-pointing bonds become the simple horizontal line of the cross. The hydroxyl group is clearly visible on the right side of that horizontal line, confirming our D configuration. This specific arrangement serves as the universal reference point for naming all other carbohydrates. Now that we have mastered a simple sugar, let us apply the Fischer rules to a much larger and more common molecule, D-glucose. Glucose is a 6-carbon sugar, meaning it has a longer vertical backbone and multiple chiral centers. We are given a Fischer projection, and our task is to mathematically prove why it is classified as the D configuration. First, we identify the total number of carbons. Since glucose is a hexose, N equals 6. Using our established rule, we subtract 1 from 6. This tells us that carbon number 5 is our reference chiral center. With our reference carbon identified, we begin our proof of the configuration. We are given a Fischer projection, where the hydroxyl groups from top to bottom on the chiral centers are positioned right, left, right, and right. Our strategy here is to ignore all the upper chiral centers. We completely ignore the hydroxyl groups on carbons 2, 3, and 4, as they do not affect this specific naming convention. We direct our attention exclusively to the 5th carbon atom down from the top of the drawn vertical chain. Concluding our proof, we look at the specific placement on that 5th carbon. The problem statement tells us that the hydroxyl group on this specific carbon is positioned on the right side of the vertical line. The right side position on this final chiral center is the key piece of information we need. Because the hydroxyl group on the highest numbered chiral center is located on the right side, this molecule is definitively classified as D-glucose. If that single hydroxyl group had been on the left, the molecule would be L-glucose, regardless of the other carbons. We have covered a lot of ground today. Let us review the key takeaways. First, Fischer Nomenclature is an elegant tool that simplifies the complex 3D world of biochemistry into manageable 2D drawings. Remember the golden rule: horizontal lines come forward and vertical lines go backward. Always place your most oxidized carbon at the top of the vertical chain. Finally, by looking at the bottommost chiral center, you can instantly classify a molecule as a D isomer or an L isomer. Mastering this visual language is your first major step toward understanding how biomolecules interact in the human body. Great work today.